SwayamPrabha. Digital India. Educated India.
Hello everyone, I welcome you all to the course on automation in manufacturing. We are starting the lecture 2 of week 3. In week 3 we are studying the selection and fabrication techniques that are required to develop an automated system. In this lecture we will be studying various terms related to the performance of a typical electromechanical system. Electromechanical system in general will be considered, but in particular the terms related to the sensor technology are discussed. The outline of this lecture is as follows. We will be studying the terms related to the performance. We will learn the definitions and look at various examples related to these terms. At the end, we will discuss the usefulness of all these terms in the selection of the variety of electromechanical systems. We are dealing with many sensors in our applications domain, but when we try to procure them or when we try to purchase them, we have to look at their characteristics. We have to choose or select a particular sensor or a transducer for our application. So, during this selection process, we have to look at certain characteristics of these sensors. These performance characteristics of the sensors are the terms related to the performance of the sensors or transducers that we will see one by one. The first term is range. So, range is defining the limits between the input that can vary by that sensor. So, if you consider a thermocouple which is used to measure the temperature, and when we say that the range of the thermocouple is from 25 to 225 degrees Celsius. So, meaning of the range is that the limits, the minimum amount of temperature that sensor can measure is 25 degrees Celsius, and the maximum amount of temperature that sensor can sense is 225 degrees Celsius. So, the range is 25 to 225, the limits between which the input can vary. The next term is span. Span is nothing but the difference between the input, the maximum value of the input and the minimum value of the input. If you take this example itself, then the span of this thermocouple is its maximum input value, that is 225 minus 25. So, here we can say the span is 200 degrees Celsius. The third term is the error. So, error is nothing but the measured value and the true value. So, the sensors are designed and manufactured in laboratory, and they are calibrated, and based on the calibration the true values are determined or the expected values are determined for a set of input parameters. When the same sensors are used in actual practice, probably they may not give the exact or the desired result. So, the value which is measured in environment or during the application will be different than the true value or the expected value or the desired value. The difference between the measured value and the true value, it is called as the error. If the sensor is giving the less error, that means it is more accurate. So, the next term of the performance of a sensor is the accuracy, which is widely used. So, the definition of the accuracy is there in front of your screen. So, we are defining the accuracy as the extent to which the value may go wrong than the expected value. So, if I am saying that the accuracy of plus or minus 2 degree Celsius, an accuracy of plus or minus 2 degree Celsius, if a thermocouple is giving me a temperature of say 25 degrees Celsius, then I can say that this 25 degrees Celsius is having an accuracy of plus or minus 2 degrees Celsius. So, meaning is that this value may have an error of up to plus or minus 2 degrees Celsius. So, it may be the exact value may be 27 degrees Celsius or it may be 23 degrees Celsius. So, with plus or minus 2 degrees Celsius the sensor is working. There is another definition of accuracy, the closeness of the agreement between actual measurement result and the true value of the measurand. So, measurand is nothing but the physical variable. So, in this case it is temperature. Often the accuracies are expressed as percentage of full range output. So, what is the meaning of that? So, if I am saying an accuracy of plus or minus 5% of full range output, let us consider an example of a thermocouple which is having a range of 0 degree Celsius to 200 degrees Celsius. So, it is maximum output is 200 degrees Celsius. So, the accuracy of plus or minus 5% of the full range output is nothing but 5% of 200 degrees Celsius. So, the accuracy of this thermocouple sensor is 10 degrees Celsius. So, whatever the values that thermocouple is sensing, they may have plus or minus 10 degrees Celsius deviation from the target value or the true value. The next performance related term of a transducer is the sensitivity. It is defined as the ratio of change in output value of a sensor to per unit change in input value that causes output change. Let us consider the example of a resistance thermometer. If there is a change in 1 degree Celsius in the environment, that instrument is reading or the instrument is giving an output of 0.5 of the ohm. So, that is called as the sensitivity. Next term or next performance related term is the repeatability or reproducibility. It is defined as the term to describe the ability to give same output for repeated applications of same input value. We are using these sensors for multiple number of times, and during these operations it is expected that the sensor should give the same answer for the similar input that we are giving, but we will not get it. So, there may be many reasons to that. It is computed as the repeatability is equal to the difference between maximum value and the minimum value given by the sensor to its full range, and that is in the percentage. So, if a sensor whose range is 0 degree Celsius to 200 degree Celsius, So, let us consider this sensor is used for a operation, and that in that operation the temperature to be measured is 90 degrees Celsius. So, during the experiments it is found that the temperature in first case it was 88 degrees Celsius, first trial, second trial it was 91 degrees Celsius, and the third trial it was 92 degrees Celsius. So, here I will consider the repeatability, in this case is 92, that is the maximum value, minus 88, that is the minimum value given, its full range. So, full range is how much? The 200 degrees Celsius into the 100. So, I will consider here, so 92 minus 88 divided by its full range into 100. So, that is coming around 4 divided by 200. So, the repeatability is 2%. The sensor is having repeatability of 2%, which is quite high. So, let us consider one more example. I can say a repeatability of plus or minus 0.01% of the full range at specific angular velocity. So, here you can consider the repeatability is very stringent, it is very high, 0.01%. The system is very accurate. Stability is defined as the ability to give the same output when used to measure a constant input over a period of time. So, let us consider example of a furnace. The continuous heating is carried out at a constant voltage, induction furnace. So, we are applying electrical field continuously, and the input is also fixed. The furnace should give a same output for a long period of time, but that will not achieve. So, that system is called as the unstable systems. So, although we are providing a uniform same input, but the system is providing different output, the output is not same. So, that is called as the system stability. There is a change in output is measured in terms of a parameter called as drift. Although we are giving a same input to the system, the output is not same, it is varying, it is diverting from its target, or the change from its target, it is called as the drifting of the output value. Dead band or the time. So, many a times what happens, the input is applied to the system, but the system will not respond to that. So, to get the initial signal or the first signal from the system, some time will get consumed. So, that response time, initial response time to get the first signal from the system, it is called as the dead band or dead time. So, length of the time from application of an input until the output begins to respond and change is nothing but the dead. So, many times when mechanical systems are being used, so to get the threshold value during the rotation, for example, in bearing we are providing angular velocity to the shafts, but to measure that angular velocity the system should come to a level, it should achieve the threshold value, and that threshold value we have to compute or we have to measure angular velocity. So, to reach that threshold value it will take some time. So, that time is called as the dead band or the dead time. The next term is the non-linearity error. The non-linearity error indicates the maximum deviation of the actual measured curve of a sensor from the ideal curve. As I mentioned earlier, the sensors are designed and manufactured in laboratories, and the designers, they are expecting an ideal behavior from the sensor. but when these sensors are used at the shop floor in real life conditions, the real life conditions are entirely different, the handling is different. So, there may be the setting errors which are borne by the human beings, there may be environmental errors, or there may be errors which are induced due to the environment or the condition in which the sensors are used. So, due to that, what may happen, we are not getting the desired result. The sensor may give us the non-linearity, it will give the different results than the exact results. So, let us take a simple example. On your screen you can see an input, say a heat flux, and an output, say temperature. So, as we increase the heat flux, there is increase in temperature. So, a sensor is designed, and ideally it is found that the sensor should give a linear relationship. So, the heat flux is having linear relationship with the temperature. This is the ideal curve, based on that the sensor is designed. However, in reality, when the sensor is used, we are getting a non-linear curve, there is no linear curve that we got. There is a difference in the input value for which we are getting the desired output value. So, ideally it is designed that when we apply a heat flux of say 60 watt per meter square, then the output of the system is giving us a temperature say around 70 degrees Celsius. But in reality, it was noted that this 70 degrees Celsius was achieved when the input value was 30 watt per meter square only. That means the system is providing the desired output at the different input value. We are getting the desired output value at the non-expected input value. So, the expected input value say 60 watt per meter square, but for 30 itself it is giving us the 70 degrees Celsius. So, the non-linearity error is the maximum difference between the input values which are producing the desired output value. So, that is nothing but the non-linearity error. So, the maximum deviation in the input per maximum full scale input. So, that is nothing but the non-linearity. So, maximum deviation in the input, so maximum deviation in the input is 30, 60 minus 30 divided by maximum full scale input. So, maximum full scale input if I consider is 200 watt per meter square. So, the maximum full scale input is 200 into percentage. So, the non-linearity is too high here, 30 divided by 200 into 100. Is about 15%. So, 15% non-linearity is error is there of that system. So, what are the reasons due to which we are getting this non-linearity error? These non-linearity errors are due to the environmental factors such as temperature, vibration, acoustic noise level and the humidity. The next performance related term is hysteresis. The hysteresis is an error of a sensor which is defined as the maximum difference in output at any measured value within the sensor specified range when approaching the point first with increasing and then with the decreasing the input parameter. So, what is the definition here? We are using certain sensor for increasing trend of the field variable to measure the response when the field variable is having increasing trend. So, let us consider the temperature itself. A sensor is used to measure the increase in temperature, say from 10 degrees Celsius to 80 degrees Celsius. So, when we are measuring for the increasing trend, we are getting a graph. So, let us consider this is a graph, a system which is showing a increasing trend when we apply a heat flux from O to P. But when we decrease the heat flux value, the temperature which was measured by the system is following a different pattern, a different way or a different path. So, that path is shown by the green color over here. So, this unusual behavior is called as the hysteresis. So, here you can see for the same input, the input value here, if we consider that the same 30 watt per meter square, for 30 watt per meter square, the temperature was measured around 40 degrees Celsius. When the sensor was used in increasing trend, it was 40 degrees Celsius. When the sensor was used during the cooling, so this we can say the heating operation, and this is the cooling operation. So, during heating we achieved 40 degrees Celsius for 30 watt per meter square. During cooling operation, the system is showing 80 degrees Celsius. The error of the output for same input value. So, there is the difference in the output for the same input value when the paths are different, so increasing trend and the decreasing trend. So, this error in the output value, it is called as the hysteresis error. Now, let us see why this hysteresis error is generated. The cause of the hysteresis error is due to the natural reluctance of a material to return to an original state after adding or removing a physical change. If we are adding or if you are increasing the temperature, or if you are putting up a pressure or we are applying a pressure and then we are removing or we are releasing the pressure, then it is expected that the system will respond the way in which it was responding when we are putting it up, when we are increasing the pressure. But due to its natural reluctance, we do not get it. So, that is called as the hysteresis. It is the natural reluctance, natural tendency of the material that is giving this hysteresis error. In addition to this natural reluctance, a certain amount of internal and external friction is also causing the hysteresis effect in the sensors and transducers. The hysteresis mainly occur in mechanical devices. There are certain phenomena such as backlash of gears, Coulomb friction and elasticity of materials are also contributing to the generation of hysteresis error. The next term associated with the performance of a sensor is the resolution. It is defined as if the input to a sensor is steadily increased from some arbitrary input value, it will be observed that the output does not change until a definite input increment is exceeded. So, this increment is called as the resolution. So, we are applying the input steadily, and when there is a change in the output is observed, the amount of input which is generating the change in the output is called as the resolution of the system. Or in other terms, we can say the smallest detectable incremental change of input parameter that can be detected in the output signal. So, this term resolution is also expressed either as a proportion of the reading with the full scale or in absolute terms. Well, my friends, let us summarize the lecture. In this lecture, we have seen the various performance related technical terms of sensors. We have seen their usefulness or application in selection of the sensors or transducers for our desired purpose, that is the development of automated system. In the next lecture, that is lecture 3 of week 3, we will study the design synthesis and design analysis phenomena, the difference between modeling and prototyping. We will look at comprehensively the utilization of computers in the designing of the prototypes, the difference between sketching and industrial drawings. We will also learn what is the meaning of two-dimensional modeling and three-dimensional geometrical modeling. At the end, we will have a short discussion on the computer-aided analysis. Thank you.